Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on March 2nd, 2026, just 5 days ago. It introduces a massive shift in database architecture, proposing that query execution code should be synthesized on the fly by large language models, rather than relying on traditionally engineered, static database engines. The paper is titled GenDB, the next generation of query processing, synthesized, not engineered. And as we'll see later, the evaluation shows some truly striking speedups over traditional systems, with exciting implications for creating highly flexible, instance-optimized databases. Figure 1 breaks down the architecture of GenDB, showing how it replaces a static database engine with a multi-agent pipeline. On the left, the system takes in the specific workload, available hardware, and user configurations. These inputs feed into the workload analyzer and the storage and index designer, which together figure out the optimal data layout. Next, the query planner and code generator map out the operations and write the actual execution code. Finally, the query optimizer runs a feedback loop to test and refine this code, ensuring maximum efficiency before deploying the final executable. So, after seeing the pipeline, Figure 2 lays out the performance results. The top row covers the TPCH benchmark, where GenDB clocks a total execution time of just 214 milliseconds, making it nearly 3 times faster than engines like DuckDB and Umbra. In the bottom row, GenDB also dominates the SEC Edgar benchmark, running about 5 times faster than DuckDB. Finally, the charts on the right show how execution time plummets during iterative optimization, with query 18 dropping over 160 times as the code is refined. Alright, while the previous figure demonstrated overall performance, Figure 3 breaks down why specific design choices matter through an ablation study. The charts compare GenDB's multi-agent approach, shown in red, against 2 single-agent configurations. Panel A on the left tracks query execution time, where the multi-agent design consistently synthesizes the fastest code across both benchmarks. Meanwhile, panels B and C track the time and monetary cost of generating that code. These results prove that structured task decomposition, by using multiple specialized agents, is crucial for efficiently building complex, high-performance query logic. So, while the previous ablation study proved the value of the multi-agent design, this generated code snippet shows the actual optimized output. For a query with 4 million distinct groups, GenDB synthesizes a shared column layout hash table. The comments reveal that the system explicitly sizes the 16 megabyte key array to fit perfectly within the available L3 memory cache. This hardware-aware approach prevents memory bottlenecks and leverages lock-free operations across 64 threads to maximize execution speed. Okay, while the previous snippet handled a high cardinality query, this generated code illustrates GenDB's approach for low cardinality scenarios, specifically TPCH query 1. Because there are only 6 distinct groups, the system synthesizes a direct array that requires just 384 bytes per thread. This tiny footprint allows the data to fit perfectly within the ultra-fast 32 kilobyte L1 cache. By using direct indexing instead of a complex hash table, this hardware-aware optimization completely eliminates hashing overhead, which drastically accelerates overall query performance. To wrap up, the biggest takeaway is that large language models can synthesize custom query code that massively outperforms traditional database engines. This points toward a future of instance-optimized databases, where systems dynamically adapt to your specific data and hardware. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.